Good morning, everybody. Hope you're all healthy and safe at home. We are coming to the end of the section 18.4 regarding Cauchy's integral formula, and thereby coming to the end of the fourth module. So in this section, we'll be discussing basically about two theorems, Lovelace's theorem and fundamental theorem of algebra. Okay, these are the two theorems that we are going to discuss in today's session. So first let us move on to Lovelace's theorem. That is, the theorem is a simple theorem. It states that the only bounded entire functions are constants. Okay, so that is, if we have any function which is bounded and entire, okay, if we have any function satisfying these two conditions, then that function has to be a constant. Okay, so we'll see how we can prove this theorem, but before proving this theorem, we shall be discussing an inequality which will lead to the proof of this theorem. Okay, so what we are going to do is, we are familiar with Cauchy's integral formula of derivatives, which is given by fn of z dot is equal to n factorial by 2 pi I into integral over c f of z by z minus z dot whole raised to n plus 1 dz, right? This was the formula. Okay, so here c was any contour. Now I'm going to suppose that c is the circle, c is a circle, modulus of z minus z dot is equal to r. Okay, then let's see what happens to modulus of fn of z dot. Okay, this will be nothing but modulus of n factorial by 2 pi I integral over c f of z by z minus z dot raised to n plus 1 into dz, right? So when I replace this modulus n factorial, that is not gonna affect. So n factorial is as it is, so is 2 pi, and we know mod of I is 1. Then the remaining term is modulus of integral over c f of z dz whole divided by z minus z dot whole raised to n plus 1. Now using the ML inequality, right, we can find a bound for the contour integral, right? Using ML inequality, that is the function is bounded by m and L is the length of the contour. So we get fn of z dot will be less than or equal to n factorial by 2 pi, and modulus integral value would be less than or equal to m into L, and L is the length of the contour. Here the contour is 2 pi r, and into what will be the modulus value of 1 by z, that will be equal to 1 by mod z minus z dot is equal to r, so modulus z whole raised to n plus 1 would be r raised to n plus 1. Okay, I hope it is clear. So just see if you want to see this. Our modulus was n factorial by 2 pi mod integral over c f of z dz. Now we know modulus of contour integral is less than or equal to m into L, where m is the bound of f of z and L is the length of the contour. And then we have modulus of z minus z dot raised to n plus 1. We know mod z minus z dot is r, so this value will be equal to r raised to n plus 1. So that is how we have obtained this inequality. So here we can cancel out the terms, and it will be nothing but m n factorial by r raised to n. So this inequality, that is modulus fn of z dot is less than or equal to m into n factorial by r raised to n, where r is the radius of the circle with center z dot, and n is the natural number, any value 1, 2, 3, etc., and m is the bound of the function. Now this inequality is called as the Cauchy's inequality. So keep in mind this Cauchy's inequality. That is, we can there can be questions like finding the bound of the higher order derivative of a complex function. So to find the bound of the higher order derivatives of the function, we have to use this Cauchy's inequality, but we must be given the value of m, r, and n respectively. So this is called as the Cauchy's inequality. Now we shall come back to our theorem, Liouville's theorem. Now what does this theorem state? This theorem states that every bounded and entire functions are always constant, right? So this is what we have to prove now. So let's see how we can prove this. So for this, let f be any bounded function, okay, which is entire. So we are assuming the conditions of the theorem now, and let me suppose that modulus of f of z is less than or equal to capital M for all z. Okay, now using our Cauchy's inequality, what can we say? Using Cauchy's inequality, okay, for just say n equal to 1, n equal to 1, what do we have? We have modulus f dash of z dot will be less than or equal to m into n is 1 here, n factorial into r raised to 1, which is nothing but m by r, right? So as r tends to infinity, so by making this value large, we can say modulus f dash of z dot tends to 0, or f dash of z dot is 0 for every point z dot in the plane, right? So we applied Cauchy's inequality for the case n is equal to 1. Now when n is equal to 1, this is the Cauchy's inequality. So we get this modulus is less than or equal to m by r. So if you make the radius arbitrarily large, we can say that the derivative tends to 0, or the derivative will be equal to 0. Now if the derivative is 0 for every point, what can I say? This implies the function f of z is constant. So the proof of Liouville's theorem is pretty much simple by using our Cauchy's inequality, and the Cauchy's inequality can also be proved in a very simple manner. So this was our Liouville's theorem, that is the only bounded entire functions are always constants. Now we shall move on to the next theorem that you have to learn. This is a fundamental theorem of algebra. This is very important. That is, if p of z is a non-constant polynomial, then the equation p of z is equal to 0 has at least one root. So we have always dealt with polynomial functions and determining their roots, right? And in the beginning itself, how did this complex number come into existence? It was by determining the roots of a polynomial. So the fundamental theorem states that if we have any polynomial, non-constant polynomial, that is important. If we have any non-constant polynomial, then the equation, that is p of z is equal to 0, okay, it will have at least one root. It will definitely have a root. Okay, it can be real, it can be complex, whatever it is, but any non-constant polynomial will always have a root. Now let's see how we can prove this fundamental theorem of algebra. For that, we are assuming we are going to prove it by contradiction. So suppose that the polynomial p of z is not 0 for any z, okay, that is, it is not equal to 0 for any z, then I am considering a new function f of z is equal to 1 divided by p of z. Now I can define this in clearly. Why? Because p of z is not 0. So if p of z is not 0, this function is clearly well defined. Also, f of z equal to 1 by p of z will be entire. It is analytic everywhere because the denominator is not 0 anywhere. So it is entire. Also, now as z tends to infinity, p of z is a polynomial, so this will also tend to infinity, and this implies what happens, f of z tends to 0, right? If we are given any polynomial, as that polynomial variable tends to infinity, the polynomial will also tend to infinity because it will become larger and larger. So as z tends to infinity, p of z tends to infinity, and if p of z tends to infinity, 1 by infinity is 0. So f of z will tend to 0. So if f of z has to tend to 0, then we can say that this function must be bounded somewhere, right? Otherwise it cannot be we cannot say that it is tending to some particular point, because if it is not bounded, then the region where the function is defined will be very large, and we cannot say that this function is tending to 0. So as f of z tends to 0, I can say that f of z must be bounded, must be a bounded function. Otherwise f of z tending to 0 is not possible. Okay, so we are having a bounded entire function. So by Liouville's theorem, f of z must be a constant, right? So I am saying that the function that we have defined by f of z is equal to 1 by p of z is a constant. So if this is a constant, p of z must be a constant, right? If f of z is a constant, then p of z also must be a constant, otherwise we cannot get a constant function. Now this is a contradiction to our assumption that p of z was a non-constant polynomial, right? In the theorem we had p of z was a non-constant polynomial. So if we suppose that p of z is not equal to 0 for any z, I can get to the conclusion that p of z must be a constant. So this is a contradiction. So therefore I can make a conclusion that is p of z is equal to 0 for some z in the complex plane, right? So this implies p of z equal to 0 has at least one root. So this was a proof of our fundamental theorem of algebra, which is very important and whose proof is very much simple using the Liouville's theorem. So the fundamental theorem is, if we are having a non-constant polynomial, then the equation p of z equal to 0 has at least one root. So that's it for today's session. Thank you. Stay home and stay safe.